Now let's look at an example of another system displaying what could be, and spoiler alert, actually is, displaying simple harmonic motion, the pendulum. A simple pendulum is just a mass suspended from a point so it can swing freely. When the mass is pushed from the central equilibrium position, it will accelerate back towards the equilibrium position, i.e. it appears to display simple harmonic motion as it is subject to a restoring force that drives the mass back. In the previous examples of simple harmonic motion, we have been examining masses on springs, where the restoring force comes from the spring constant. In this example, the pendulum, the restoring force is instead driven by gravity. However, remember that in order to use the physics of simple harmonic motion, the restoring force must be linear, i.e. it must follow Hooke's law. So we need to find out if there is a constant that can describe the system like the spring constant K. So first, let's draw the pendulum and examine the forces on the mass. Here is our pendulum. A bob is attached to the string L and has a mass m, and we'll define the angle here as theta. The pendulum will swing back towards the central location, and inertia will keep it going, and it will swing back and forth like this. Now consider the forces. I'll just copy the pendulum over here and remove the bits of the drawing we don't need. Okay, so there were two forces acting on the mass. We have the tension in the string T and the weight of the bob mg. The motion is along a circular path with a short arc length as shown. If we break up the weight force into the components along the coordinate system defined by the tension, we will see something like this. Fy is here and Fx is here. Before we solve for Fy and Fx, I'll draw the triangle out again up here so we can see it more clearly. This is mg, Fy and Fx, and here is theta. Now we can solve for Fy. mg cos theta, and do the same thing for Fx, which of course equals mg sine theta. Now we can define the directions of the forces. We see that this will be negative. So Fy equals minus mg cos theta, and if we have a look at our free body diagram, we can see that this is balanced by the tension T, because we have no movement in the y direction. So our total force must be just equal to the x component, Fx. And this is equal to Fx equals minus mg sine theta. This is the restoring force that is pulling the mass back down to the equilibrium position. A reminder that if we can show that this restoring force is directly proportional to the displacement, i.e. we have a version of Hooke's law, then we have a simple harmonic oscillator. But at this stage we have a trigonometric relation, and this is not what we want. But we can use what's called the small angle approximation, where sine theta for small angles simply equals theta, and this has to be in radians. This is for small angles less than about 15 degrees, and the number needs to be in radians. Using this, we can write that Fx equals mg theta. Let's copy this relation out again. Fx equals minus mg sine theta, which using the small angle approximation simply equals minus mg theta. Now we need to use another useful mass relationship, this time relating the arc length to the radius and angle in radians. The arc distance, let's call this s, is directly proportional to the angle theta. When theta is expressed in radians, the arc length of a circle is related to its radius, which is L in this example. So we have theta equals S on L. Let's look again at our force formula and notice that we can drop the subscript x, as this is really our total force. So we can write out F equals minus mg, and instead of theta we'll replace that with S on L. We can rewrite this to give us some more physical insight as F equals minus mg on L S. And this looks a lot like Hooke's law. S is the distance or extension, and mg on L is a constant. A reminder, Hooke's law equals F equals minus kx, where k, in this case, for the pendulum, is mg on L, and S is x. This shows that we can express the physics of a simple pendulum using the simple harmonic motion relations. Now let's use this value of k to learn something interesting about our pendulum. What would we like to know? Well, the timing comes to mind, the frequency, or perhaps more usefully, the period of oscillations. You may remember that period is denoted as big T and is measured in seconds. So we have everything we need to find T. We have our restoring force function, let's write it down again, and we have expressions for the angular frequency omega that we will need. Remember, omega equals the square root of k on m, and also equals 2 pi on t, the period. Now we just found a value of k, which equals gm on L, so let's put that in here and see that omega equals the square root of g on L for a simple pendulum. Now let's find an expression for the period t of the pendulum. So omega equals 2 pi on t, and omega also equals g on L. So if we put these two equations together and rearrange, we can solve for t. And here is our result. The period of a pendulum swing is 2 pi, the square root of L on g. This is amazing, as the period only depends on the length and g, and does not depend on the mass of the pendulum bob, m, or the amplitude. The story is that Galileo noticed a slight swing of a lamp suspended from the ceiling of the cathedral during a service in 1582. This is the lamp that's currently hung in the cathedral in Pisa, where Galileo first noticed this phenomenon. It's right next to, of course, the Leaning Tower of Pisa, where he did some other things. Galileo is said to have timed the period of the lamp using his own heartbeat as a timing device. He noted, just from careful observation, that the period of the swing was independent of the arc through which the lamp travelled, and indeed that's just what we've shown.